Get way too big and way too bulky. So good thing to remember. Congrats on making it to the end. In this course, you're going to learn all the basics that you need to know about Apache Spark, like the architecture, what does the driver do, what does the executor do, how does it all come together, why is it so powerful, and when should you pick Spark over something else. These basics are going to be covered in the course, and then later on we are going to go into a hands-on lab to just talk about partitioning and sorting and how to actually have Spark read and write data. You will get a lot of hands-on knowledge in this course. Make sure to download Spark in the description below, and if you're interested in learning how to use Spark in the cloud, I highly recommend checking out the Data Expert Academy. You can get 20% off in the discount below. I'm excited to see you there. Okay, so Spark is a distributed compute framework that allows you together? Why is it? And when should you pick Spark? You to process very large amounts of data efficiently. Some of y'all probably knew that. It's kind of the successor to other technologies. If y'all followed any of like the progression of big data technologies, really everything started back with like Hadoop and Java MapReduce back in like 2009, and that's when those things were developed. And then we learned, and then they kind of transitioned to Hive, and then now Spark, and Spark is kind of winning, and like it's gonna be wild to see how long Spark actually sticks around, because it looks like it has a longer kind of technology curve than some of the other predecessors. But that's essentially what Spark is. We're going to go way more deep into the details of Spark here, but that's the idea. So I just want to talk a little bit about the details. Details of Spark here, but that's the idea. So I just want to talk a little bit about my history with Spark. So I learned Java MapReduce back in 2014 when I was working at Teradata, and then 2015 to 2017 I used Hive a lot at Facebook, a lot at Teradata, and then I remember in 2017 there was a big push at Facebook to adopt Presto, to switch Hive to Presto. But the problem with Presto back then, and still is kind of a problem with Presto now, is Presto does everything in memory. And so if you have an operation that can't fit in memory, Presto just fails. You can't use it. And so, and I worked in notifications at Facebook, so we couldn't use Presto. But I also didn't want to use Hive because Hive was slow and terrible. So like I was one of the very first early adopters of Spark at Facebook. I think I was like the third or fourth person to like create a Spark job at Facebook. And it was great. It was a slam dunk in so many different places in my usage, both at Facebook and further on in my career. I've tried all the different APIs for Spark, right? There's Spark SQL, there's DataFrame, Dataset, PySpark, Spark R. Like, I always joke with people about Spark R because people forget that you can actually write R code with Spark, and it's kind of crazy. But anyways, I attribute learning this technology as one of the main reasons why I was wildly successful in big tech, because I learned this framework very, very thoroughly, and I know all the ins and outs of it. And so it's been great. I've been using it since then, like since 2017 to 2023. So like so many years, like six years of just using Spark, and it's just gotten better and better and better since then. And yeah, let's keep going here. So why is Spark so good? There's a couple things. Spark is really good because it leverages RAM more efficiently and more effectively than previous iterations. So for example, like if you wanted to do a group by computation in Hive or MapReduce, everything had to be written to disk, and then written to disk and read from disk, and every single step had to be written and read from disk. And it made it very resilient. Like Hive and Java MapReduce jobs were very resilient, but they were also incredibly painfully slow. Spark was able to kind of short circuit some of that and minimize the amount of times that it needs to write to disk. Spark essentially only writes to disk when it has an operation that it doesn't have enough memory for, and then it will do this thing called spilling to disk. Generally speaking, though, like you don't want Spark to spill to disk. You want Spark to use RAM as much as it possibly can, and that's going to be where you get very effective and fast computations with Spark. Spilling to disk makes Spark, it essentially has Spark go back to being Hive, and it's, again, being kind of slow. So another thing about Spark is it's storage agnostic. Like, you can read whatever you want, right? Whether it be a relational database, a data lake, a file, MongoDB, whatever you want to read, Spark can read it easily. Also, Spark has a massive, massive, massive community. And you don't need to use Spark with Databricks. You can use Spark with whatever technology you want, and it works great. So that's pretty much what is going on with like why Spark is so good. When is Spark not so good? There's going to be, I think, two cases when I would say that you don't want to use Spark. The first one is similar. It's a very similar guidance to what I said about Flink. Was if you're the only one on your team that knows Spark, then like you probably shouldn't use Spark. You should, or you should teach your team so that you can have better maintenance and better reliability, and you can distribute responsibility more effectively. And also, your company might already use something else. Like a lot of companies bet heavily on BigQuery, or they bet heavily on Snowflake, or they bet heavily on another kind of technology that isn't Spark but also works. And in those cases, like, it's better to have 20 BigQuery pipelines than it is to have 19 BigQuery pipelines and one Spark pipeline. Like, it's just like homogeneity of pipelines matters a lot. I've used that word a couple times in some of these presentations, and that's when like you don't want to bring in Spark in those cases. You want to just use what the company's betting on. Okay, so how does Spark work? So I like to use the analogy of Spark as like a basketball team. So the basketball team has three things in it. It has the plan, which is the play that the basketball team runs. The driver is like the coach of the basketball team, and the executors are the players of the basketball team. So we're going to be kind of using more analogies here. I need to update these slides so they actually have like basketball players in them, but it'll make a lot more sense as we kind of go through this. So remember, we have the play, the coach, and the players. And those are going to be the three things that we have, but they're called the plan, the driver, and the executors. Okay, so the plan. You can think of this as the play. This is like the coach will tell the players what play to do. And this is going to happen like where the play can be described in whatever way you want to do it, whether usually it's going to be Python, Scala, or SQL, or R if you want to be a weirdo. And then the plan is evaluated lazily. What that means is the plan doesn't actually run until I like to say like a player takes a shot, which means like they either like try to write data out somewhere, or they try to collect data somewhere. So that's what taking a shot means, like writing output or collecting data. And the collect, what that means is like essentially they are taking information from the play and bringing it back to the coach to have the coach tell them what to do next. And that's going to be the main things around the plan of how Spark works. So this is going to be like your data frame code. This is going to be your Spark SQL. This is going to be your data set API code. And that's essentially what we're going to be working with here. So that is kind of the plan of how Spark works. Okay, so you have the driver, which is like the coach. You can think of like the coach reads the plan. So the coach like tries to figure out what plan to run and what play to make. And Spark only, like, so you the driver can have a couple settings that it can have in it, but there's like probably 10 different driver settings for Spark that you can set. Really, there's only two that you need to care about here. Spark.driver.memory, which is going to be the amount of memory that the driver has to process the job. I think this defaults to like 2 gigabytes. It can go all the way up to 16. Generally speaking, the only times that you need to bump it up is like if you have a crazy complicated job that has like so many steps and plans, you might need to bump it up in that case. Or if you do collect where like the data that the job is processing changes the plan of the job, which mostly is bad practice. You don't, generally speaking, want to do that. There is some edge cases where you want to do that, but like for the most part, you don't want to do that. But those are going to be the only two cases when you really need to bump this setting up from 2 gigs to whatever other number you want to bump it to. The only other one that you might want to also change is memory overhead. So this is where the driver needs memory to process the plan. And if for some reason you have a very complicated plan, you might need more overhead memory because the JVM might take up more memory in those cases. So you might want to crank this to a different number. which is so that your non-heap memory is the memory that Java needs to run, not like the memory for the plan or the memory for the collect calls or the memory for anything like that. It's none of that. It's just the memory that Java needs to run. And the only time that needs to be bumped up is if you have a very complex job. Every other driver setting you shouldn't touch, at least in my experience. I've spent many years. I've been playing around with Spark for 7 years, and I've played with all of these settings just to see, played a lot of what if and science and experimentation games with a lot of these settings. And these are the only two that I've seen that have any sort of substantial impact on the performance of the job. All right, so that's the driver. So keeping in mind, the driver determines a few things for you. So the driver determines when the job should actually execute. So that's like when it finds like an output or a collect call. It will find those to tell the players to start running the play. It will also figure out how to join the data sets, which can be very important. Because depending on what type of join Spark decides to use, that can mean that your job is 10 times less performant or 10 times more performant. And it also determines how much parallelism is needed in each step. So for example, if say you have two data sets you're reading in, and then you join those two data sets. And neither data set is small. You have two big data sets you're reading in. So generally speaking, the initial parallelism for those steps is how many files those data sets are written to. And then when you join, then you get into the parallelism step, which we're going to talk about here in a second. And that is how much parallelism happens after a join or something like that. And so those are the three things that the driver really is all about. And if you can get the driver to do these things the right way, then you can have way more efficient Spark jobs. So let's talk a little bit about the executors. Executors here are going to be what actually do the work. These are like the Michael Jordans and the Kobe Bryants and the LeBron Jameses of the Spark framework. And they actually do the work. They're the ones who actually take in the data and then transform the data and filter and aggregate and whatever other operations you want to do on the data. So in this case, there's really only about 3 settings here that you want to touch in terms of executor settings. In this case, you have Spark executor memory. This is, again, has the same constraints as driver memory. So it defaults to like 1 or 2 gigs, and then it can go all the way up to 16 gigs. I've seen bad practice with this actually, where there's like, if a job like OOMs, or out of memory exception, one of the things that can happen here is people will update this to 16 gigs and then just forget about it. And they're like, whatever, like it's fine, even though like it makes it so the job, it runs way more expensively. Generally speaking, the way I like to think of like how to set your executor memory is you want to try running it at a couple different memory levels, like running it at like 2, 4, 6, 8, something like that. And then one of them is going to run all the time. And once you have the one that runs all the time for like a couple days, that's the smallest number that runs all the time for a couple days is the kind of way that I like to figure out the right number here. Because one of the things that's tricky about this is you don't want to have too much padding, because if you have too much padding, you're just wasting all this memory. But you also don't want to have too little padding, because then the chance of like out of memory is annoying. And when things break, like engineering time is one of the most expensive things for like a company. Data engineering time, like your actual time, is more expensive than the cloud costs of a little bit extra memory usage. Like a little bit of wasted memory usage is going to be worth the trade-off of your actual time on the job. So that's the way I like to think about it. But I also am against just setting it to 16 gigs and then just setting all jobs to 16 gigs and calling it a day, because I think that that's terrible. Then you have executor cores. So generally speaking, an executor can take 4 tasks at once. You can go up higher to 6. I would say you can go all the way up to 6 if you want. And then this makes it so that you can get more parallelism per executor. But if you have more than 6, the thing that happens is you get a different bottleneck, right? The bottleneck in that case is the executor disk and the throughput between like when tasks finish. And so you don't want to crank this up higher than 6, because you end up bottlenecking yourself by the throughput of too many tasks running at the same time. And so generally speaking, you want it to be 4. I don't generally touch this setting. I've seen people touch this setting and see some results, but generally speaking, I don't touch this. But maybe crank it to 5 or 6 if you want to get a little bit more parallelism, make your job a little bit faster. But more than that, like, it's a trade-off, right? You can't just crank this up to like 1,000 or something like that, because obviously your executor doesn't have 1,000 cores to begin with. But maybe you can leverage a couple more. You want to be careful there too, because like if you crank it up to 6, then you have 6 tasks on one executor, and it also makes it more likely to OOM, because depending on the memory footprint of each of those tasks, if they're all running at the same time, then it's more likely to OOM, because the probability that you get you have 6 tasks that are skewed a little bit more is higher than if you have 4 tasks that are skewed. So that's just another thing to think about. And then you have the memory overhead, just like you have with the driver. In this case, you really want to maybe bump this number up if you have jobs that have a lot of UDFs, especially like if you're using PySpark. PySpark UDFs are terrible.
and just UDF's a lot of complexity, a lot of joins and unions and all sorts of, like, if the plan is crazy and like you need, your JVM might need a little bit more of the memory footprint. The thing about this is, I like about the memory overhead, is that you can increase the memory overhead without increasing the memory itself. You can make the job more reliable at no additional cost. So that's the thing I like about these overhead settings, is that they can actually make a difference. So definitely try them out. It's a lot of complexity, a lot of joins and unions and all sorts of, like, if the plan is crazy and like you need, your JVM might need a little bit more of the memory footprint. The thing about this is, I like about the memory overhead, is that you can increase the memory overhead without increasing the memory itself. You can make the job more reliable. At bucket of the second table, and file 1 is the first throughput of too many tasks. Up to task number up if you have jobs that have a lot of memory itself. You can make the job more reliable at no additional cost. So that's the thing I like about these overhead settings, is that they can actually make a difference. So definitely try them out, especially if you have a job that's a little bit unreliable. That's a good kind of setting that you might want to fiddle with. So remember, we're going back to the analogy real quick. So we have the plan, which is the play that the players make. You have the driver, which is like the coach, and you have the executors that are the players that actually run the play. All right, this is a very, very important slide in Spark here. So generally speaking, you get there's essentially 3 types of joins in Spark. You have shuffle, sort, merge join, broadcast hash join, and bucket join. These are going to be your 3 joins that are important. Shuffle, sort, merge join is going to be the least performant. Broadcast hash join and bucket join are going to be a little bit more performant. But shuffle, sort, merge join is also useful because it's the most versatile, because it works pretty much no matter what. Whereas broadcast and bucket join work under very specific circumstances. So broadcast hash join works when one side of the join is small. And it actually doesn't have to be the left side of the join. It's just one side of the join needs to be small. And then it works pretty well, because in that case, instead of shuffling the join, it just ships the whole data set to the executor, and you don't have to shuffle at all. And it works great. So broadcast hash join works when one side of the join is small, and it actually doesn't have to be the left side of the join. It's just one side of the join needs to be small, and then it works pretty well, because in that case, instead of shuffling the join, it just ships the whole data set to the executor, and you don't have to shuffle at all. And it works great for small-ish amounts of data. Like, I've been able to broadcast up to like 8 to 10 gigs. If you try to broadcast more than that, you're going to bump into problems with executor memory at some point. So that's a thing to think about when you're determining which joins to pick. Bucket joins are going to be where, if you want to do a join without shuffle, you can do that with a bucket join. I have some diagrams in some future slides that will kind of explain more about like how this works. But so you have shuffle, sort, merge join, broadcast hash join, and bucket join. And being able, like in Spark, you use .explain, and it's going to bring up these words. So you need to know what each one of these words means if you want to be able to optimize your Spark jobs. Generally speaking, you want to minimize the amount of times you use shuffle, sort, merge, join. That is a very hard word to say, too many S's. But broadcast and bucket joins are going to be your best friends in a lot of cases. So so let's just talk about shuffle real quick, because I think shuffle is an important part of this puzzle. So shuffle is going to be like the least scalable part of Spark. That's the thing. Like, and like the more you shuffle, and as scale goes up, the usage of shuffle is just gets more and more painful. And it gets to a point when, like, once you're over like 20 or 30 terabytes, if you're trying to process more than 20 or 30 terabytes a day, then shuffle just goes out the window, and you can't do it. You got to solve the problem in a different way. So, anyways, you can think of like imagine you had a job that you have a table that you're reading in, and it has 4 files. And what we're going to do is we're going to do a map operation first. Maybe we add a column or we filter it down. So map operations here are going to be where, or you add a column, like you add a new column to it. You like select star, comma, and then you add another column, or like dot with column if you're using like the data frame API, and then you add columns. And then and the thing about that is it's infinitely scalable for the most part. It's scalable to the number of files, and you don't have to do anything, and you don't have to shuffle. But then what happens is, like, imagine then you need a group by. So in this case, we're saying that there's 3 partitions in Spark. The default is actually 200, but I didn't want to build a diagram with 200 squares, so this is just kind of a simplified view of this. But what ends up happening is, imagine you have you're grouping on user ID in this example here, and then everything in file 1, all the user IDs, if they you divide the user ID by 3. And then you look at the remainder. If the remainder is 0, it goes to partition 1. If the remainder is 1, it goes to partition 2. If the remainder is 2, it goes to partition 3. And same thing happens for file 2, file 3, and file 4. And so all the data from file 4 will be kind of in files, will be in partition 1, partition 2, and partition 3, depending on where they're at. So this is how shuffle works, and this is how, like, if you imagine on both sides, so this is just like a group by operation in this case, but if imagine instead you were doing a join where files 1 and 2 were part of one table and files 3 and 4 were part of another table, and then you want to join them together, then you can do that the same way, because then they'll shuffle, and then all the data, like all the user IDs that are divisible by 3 go here. Right, and then you get all the right data in each partition, and then you can do the comparisons. And then you can actually do the join on the data with the relevant data there. So that's essentially how this is the default case. This is going to be that shuffle, sort, merge, join. That's going to be how that works, right? So the difference here for if you're working with like a broadcast join is, instead, you don't even need to shuffle, because what you can do is the broadcast join can just, files 3 and 4 are small enough that you can just ship all of the data to each of these executors, to file 1 and file 2, and then they can do all the comparison and all that stuff in this spot, so they don't have to do any shuffling at all. And that can be a very powerful way to go about things. Anyways, we're gonna go back to this slide in a second because I want to talk more about buckets. But let's go a little bit deeper into this presentation. So, shuffle partitions and parallelism are linked. They are actually the same thing. It's kind of weird. Like, Spark is so weird because it has these 2 settings: as spark.sql.shuffle.partitions and spark.default.parallelism, and they are, for the most part, the exact same thing. Unless there is one tiny exception, and that's like if you are using the RDD API directly, then spark.default.parallelism is the setting to use there. But if you're using anything else, data frame, Spark SQL, dataset API, any higher level API, which you should be doing, don't use the RDD API. Like you should almost never, ever be using the RDD API. There might be a small, tiny edge case where you should, but like 99% of the time, you should not use the RDD API. You should be using the higher level APIs. That's guidance from Databricks and from Spark as well. So these shuffle partitions are linked with parallelism. This is essentially, if you go back to this slide here, this is the number of partitions that you get after you do a join or a group by. So let's talk a little bit about shuffle. So is shuffle good or bad? I think so far in this presentation, you might be considering shuffle is kind of bad. Shuffle is probably not what we want. And I don't agree with that. I think that shuffle is actually pretty decent. That like you should probably use shuffle in most cases, especially if the volume is not really high. In this case, I'm saying volume being greater than 10 terabytes. Even 1 terabyte shuffling is pretty decent. And so I have an example here I want to go over real quick, and I'll send you guys the link to this. There's some writing online about it as well. But so one of the pipelines I worked on in Spark, this is the biggest pipeline I ever worked on in my entire career, was it processed about 100 terabytes an hour in Spark, and we had to do a join. And so what we needed to do was every row in this data set was a network request. It was every network request that Netflix received, and we wanted to join that data set with a data set that mapped that network request's IP to a microservice app. Like, because Netflix has thousands of microservices inside of its architecture, and we wanted to figure out which IP, like where was this request coming and where was it going, just so we could see like which app is talking to which app. That was the whole idea behind this pipeline. And so one of the things that was nice about that was we were actually able to ship all that lookup table, that IP lookup table. We were able to get it down to like, several gigabytes, and we were able to broadcast join it, and it worked. Then a new requirement showed up for that pipeline, and that was because Netflix wanted to upgrade all of their services to IPv6 instead of IPv4. Then at that point, we were trying to ship things over in IPv6. And I don't know if y'all know, but IPv6 is, I think, 100 or 200 or it's like 100 or 1,000 or 10,000 times more IP addresses than IPv4. So it goes from like billions to like quintillions or something like that. Like it's a very, very much bigger search space. So when we tried to move notifications where we had to join two tables. So let's talk about the notification one first. So for the notification data sets that we're joining at that very at that cardinality down there, like instead of doing a shuffle sort merge join, we bucketed the table of the buckets. And then what we did with that was then when you do the join, you can do the join without shuffle, because if you go back to forward, because in that case, when everything's bucketed, you don't like the files already they already have the guarantee that the data, all the data that you're looking for based on that ID already exists in that file. You already have that guarantee because it's bucketed, and that's what the files, essentially how you write the files is based on the user ID. You modulo the user ID, and then you write the buckets out. And then when you do the join, you just match up the buckets. So in this case, imagine you had two tables and they both had two buckets, and they were both bucketed on user ID. Then instead of having to map like file 1 to partition 1, 2, and 3, and file 2 to 1, 2, and 3, what you could do is you would just line up file 1 and file 3, because file 3 is the first bucket of the second table, and file 1 is the first bucket of the first table. And you essentially just line up the buckets, and then everything works, and then you don't have to shuffle at all. And you get a massive, massive, massive performance gain if you do that with buckets. And interestingly enough, you can actually, even if the two tables don't have the same number of buckets, you can still do a bucket join, assuming that they are multiples of each other. So imagine in this case, instead, we had one table had one bucket and the other table had 2 buckets, or you can think of like 2 and 4 or 4 and 8. Well, in that case, like files 1 and 2 would have all of the data in files 3, because like it would be, all of it would line up because they're multiples of each other. So the big lesson here is that when you're bucketing your tables, always bucket your tables on powers of 2. Always use powers of 2. Don't be weird and be like, I want 7 buckets or like 13 buckets or something like that, because then like the only way that you can get a bucket join is if the other side also has 13 buckets, and that might not be the case. Like and so one of the, I think, bigger questions here is like, how do you pick the number of buckets? Well, in some of these cases, it's based on the volume of the data, right? And then you want to kind of divide it where it's like, okay, I know for like at Facebook, like we had 10 terabytes. And so you're like, okay, 1,024 buckets. We were like shooting for like, in that case, I think like 10 gigs a bucket or something like that. That was kind of the idea. But like, there's kind of a rule of thumb there where like, because if you have too many buckets on data that's too small, then you have that same problem where there might not be any data in one of the buckets because of the modulo problem, where like, if say you have like 1,000 rows and you're like, okay, I'm going to bucket this into 1,024 buckets, then you're guaranteed in that case to have 24 empty buckets by the, I don't know if y'all know that, the pigeonhole principle in combinatorics, but you're guaranteed to not have enough data in one of the buckets. And if you have an empty file, that can mess up with a lot of these systems, and it doesn't trigger the bucket join the right way. So like, that's where you want to make sure that like you aren't putting too many buckets on tables that are small. That's just kind of an aside. So that's how I solved the problem at Facebook. But what about the problem at Netflix? That problem was different. So one of the things about that problem was bucketing the 100 terabytes an hour was going to be very expensive anyways. So because bigger scales, that's usually how you solve the problem. We're going to talk a little bit about minimizing downstreams. I talked a bit about this already, but bucket the data if multiple joins or aggregations are happening downstream. Bucketing is great, but like if you're bucketing and you're only doing one join, then usually that's a waste, because like you have to pay the shuffle cost already to bucket. That's the cost, because you have to, in order to write to a bucketed table, you have to put that in there. You have to already have that in there. So and then if you're only doing one join with it, then like, why are you doing that? you really only get benefits from bucketing is if you are doing multiple joins with these tables, because then that's when you're going to really see the big benefit. So that's a good thing. Remember, the one thing about bucket joins that I want to talk about is Presto can be weird with bucketed tables, because especially if you have tables that have a small number of buckets, maybe it's like 8 or 16 or something like that. Then when you query stuff with Presto, like the query might be slower because the initial parallelism will always be 16, and like maybe Presto wanted more. And like when it's a non-bucketed table, it can split the files up and it can like handle it better. But generally speaking, I like buckets. Buckets are good. And the last thing I wanted to say is that if you're playing around with buckets, always use powers of 2, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, just powers of 2. Always use powers of 2. So minimizing shuffle is, I would say, one of the most important things that I did in my career that has helped me move up the ladder, because you can save a lot of money, especially at big scales with this. Okay, let's talk about shuffle and skew. Skew is another one that I noticed that was also I had to deal, like, skew's gotten so much better though. Oh man, like y'all are lucky. I feel like this is one of those, like, back in my day, like things were difficult, right? So so skew happens when you partition your data, right? Where you have that modulus thing, right? Where you divide by 200 and then you split up all the data. And the problem happens, right, is where one of those 200 partitions has way more data than the other partitions. Like, what you can imagine in this case is, like, imagine if, like, Beyonce and Justin Bieber and, like, I don't know, like, The Rock, they all somehow miraculously all of their user IDs are divisible by 200. And then what happens is every single time all of their notifications go to the same executor, and then it's like them and then like a bunch of random people, and then like, but just those 3 users are going to have dramatically more data than everybody else because they're famous. And so they're going to skew. That one executor is just going to be given, like, I don't know, 10 or 100. Another symptom that can happen here is your jobs will get to 99% and then fail. That is probably the most infuriating thing about data engineering in my mind, like, at least from a technical perspective, is like skew is like such an asshole, because it's like, okay, we're gonna almost run, we're gonna let your job run for 2 hours and then fail, and then you're like, why did it fail? Like, come on, right? And so that is why I don't like skew. But things have gotten a lot better with skew, and we're gonna talk a little bit more about how to solve these problems. So how to tell if your data is skewed, right? I was talking about this. The most common symptom is your job is going to get to 99%, and it's going to take 1,000,000 years, way longer than you expect the job to take, and then it will just fail. And it's sad. because you're like, wow, why did it fail? Another more scientific way is you can actually like do a box and whiskers plot and actually like map it out and do it like a data sciencey way. I've literally never done that, but if you want to do that, you can do that and like have more confidence that your data is skewed. I almost always just like build my pipeline and then get mad when it fails at 99% and just like kind of do it the hard way and not the scientific way. But that's how you want to know. Tell if your data is skewed. Let's talk about how you can actually solve this problem. Okay, so the most effective way to solve this problem is, but it's only available in Spark 3, and we're going to talk about it real quick, is you need to set this spark.sql.adaptive.enabled and just set it to true, and that will solve your problem. Done. Like, you don't have to do anything else. It's amazing. Like, I love this setting because then you don't have to do all like. Well, I'm going to talk about one of the ways that you can do it if you don't have Spark 3 and you have a skewed group by. This doesn't work with a skewed join, but it works with a skewed group by, where what you do is you essentially you add a column, which is just like a random number, because then what that does is it will break up the skew, because then some of the skew will go to one executor, some will go to another executor, and then you essentially do two aggregations where you aggregate once where you group by the random number, and then and that gives you like a partial aggregation, and then all the skewed data will be small at that point because it will all be back down to like whatever your group by grain is, and then you aggregate again and you just remove the random number and sum everything up again. So you do two sums, and that will give you the same thing as you would get otherwise. So you want to be careful using this. I don't know if y'all remember from a previous presentation, I talked about additive and non-additive dimensions. And this is a great example of where additive and non-additive dimensions can mess you up. Because if you sum something twice like this, they might not actually add up to the same number. But it depends on or add up to the correct number, and it depends on the dimensions. But generally speaking, most dimensions are additive. I think like about 80-90% of dimensions are additive, and so you can use this and it works great. But make sure that you are aware of that before you use something like this. But generally, just use spark.sql.adaptive.enabled. Obviously, don't just set this to true all the time, like just in case, because it makes the job more expensive to run, because Spark has to compute all these but it depends on or add up to the correct number, and it depends on the dimensions. But generally speaking, most dimensions are additive. I think like about 80-90% of dimensions are additive, and so you can use this and it works great. But make sure that you are aware of that before you use something like this. But generally, just use spark.sql.adaptive.enabled. Obviously, don't just set this to true all the time, like just in case, because it makes the job more expensive to run, because Spark has to compute all these like extra statistics about the job while it's running, and that you don't get those all the time, like just in case, because it makes the job more expensive to run, because Spark has to compute all these like extra statistics about the job while it's running, and that you don't get those for free. And it makes the job slower, but it makes the job more resilient to skew. And so that's why it's great. And hopefully y'all are just on Spark 3, so you don't have to do this like random salting hack. I want to talk about one more way to deal with skew in joins. And this is what I did at Facebook was if you have a join, the problem is like you can't have this like random number thing. It doesn't work the same way. And so what I did in that case was I identified the outliers and like just filtered them out. and then just was like, okay, we don't need these IDs. And then I was like, Beyonce can just wait. They can wait and have data tomorrow. And sometimes that is an acceptable way to deal with skew, is you filter out the outliers. Or what you do is you partition your downstream table where you have one side of the pipeline that processes everybody else, and then you have the other side of the pipeline that processes the outliers. And in that case, you can usually that can usually work pretty well. So that's another way that you can kind of manage stuff. But those are essentially the main ways to deal with skew. Okay, let's talk a little bit about the ways Spark is kind of ran. Y'all know we were going to use Spark on Databricks, and then it kind of fell through. But Spark on Databricks and Spark unmanaged Spark kind of have different ways that you want to run and test your job. So generally speaking, should you use like a PySpark notebook when you're running your job? This is something I remember back in 2018 when I was working at Netflix, and then they got this working because Netflix kind of pioneered the idea of running notebooks in production. And I was like, I still don't like it. I still don't like it at all. I don't like the idea of running notebooks in production because it's like unchecked mutations. You're not using Git. Like, there's a lot of problems with it. But Databricks, like, they all are about it. Like, that's what the whole UI is all about. They really want you to use notebooks, right? Databricks are all about it. So, but in big tech, you should probably only use notebooks for proof of concept, and then check your Spark code into like a Git repo. And then you're going to use this thing called Spark Submit from the CLI in big tech, whereas like you can just run the notebook in Databricks. So that's kind of like the difference between Spark on Databricks and regular Spark, like thinking about like kind of best practices. I personally like unmanaged Spark using Git and Spark Submit for my jobs. I'm kind of anti-notebook because I feel like notebooks, they don't invite unit tests, and they don't invite integration tests, and they don't invite good engineering best practices. But they invite less technical people. Like, they invite people who don't have all of the technical things and allow them to actually leverage Spark. So that's where they're useful, is they actually allow people to use Spark and they don't have to be so technical. So that's why they have adoption. But as data engineers, I generally think that it's like not the right way to go. I'm kind of anti-notebook because I feel like notebooks, they don't invite unit tests, and they don't invite integration tests, and they don't invite good engineering best practices. But they invite less technical people. Like, they invite people who don't have all of the technical things and allow them to actually leverage Spark. So that's where they're useful, is they actually allow people to use Spark and they don't have to be so technical. So that's why they have adoption. But as data engineers, I generally think that it's like not the right way to go. So anyways, that's Spark on Databricks versus regular Spark. I just like to call that out. So remember I was talking about all those different types of joins. One of the big things that you want to do, and we're going to check this out a little bit today in class, is we're going to look at this .explain. So you can look at Spark will actually tell you everything that you want to know about it if you use the explain in your data frames. And that's going to give you a lot more insight into actually how Spark is running underneath the hood. Definitely check it out. It's very similar to like explain in SQL. You could actually, I'm pretty sure you can use Spark in Spark SQL like the same way, where you put like explain at the front. Okay, another thing just talk about is like, where can Spark read data from? I'm sure y'all know, just like the answer here is everywhere for the most part, like from the Lake, Delta Lake, Apache Iceberg, Hive Metastore, Postgres, Oracle, REST API calls. You want to be careful. I think that's one of the things here I want to talk about real quick is like when you make a REST API call, it's almost always done in the driver. And remember your driver memory settings. So like if you are making your REST API call and the response, or you're making many API calls and the responses are big, then you want to be careful how you're processing that data in Spark, because it is a lot more prone to running out of memory. So and in those cases, like a lot of times you might want to like parallelize them. So like what you can do is like you get a list of URLs and then you do spark.parallelize, and then you essentially make the API calls in the executor. It's a trade-off though, because the nastiness of that is then you essentially hammer the API in parallel, and that can be a problem, and that's like a separate problem versus like managing all the memory in the driver. And those are two separate problems that I find. So for me, I generally find APIs to like not be very like REST APIs. I don't find them to be very Spark friendly unless it's like if it's like one call, then usually it's like whatever. But if you're making a lot of calls, Spark might not be the right way to do it. So that's a thing to think about. Like a lot of times, like the way that Spark likes to do it is instead of calling and hitting the REST API, they like to read directly from like the Postgres database or the inner guts. They like to essentially bypass the API and read directly from the data tables. And Spark's going to have a way nicer time doing that than reading from an API. So definitely know that whenever you're doing your integrations, that's probably going to be the smoother integration, is like where you go up a layer and you read from the data tables as opposed to trying to read from the API. And obviously flat files. We're going to be using flat files today in the lab. So that's pretty much it for how Spark can read data. So Spark output data sets. Almost all data sets in Spark, when you output them, should be partitioned on date. This date should be the execution date of the pipeline, which is like, if y'all use Airflow, there's like it's like curly brace DS, curly brace. Like it's like that is like the param. It's like the date that you want to backfill or the date that you want to run the pipeline for. That date should be passed to Spark, and then Spark can write the right data accordingly. DS partitioning is very powerful. Definitely look that up if you're not familiar with that, because if you're not partitioning on date, like your tables are going to get way too big and way too bulky. So good thing to remember.
Congrats on making it to the end of the Spark Basics lecture. If you're taking